This is the presentation of the structural analysis we made on the Neue nationalgalerie, made by Mies in 1968. And as you see here, the building is very symmetrical, and what it has 8 cruciform columns that supports all of the weights, and it has huge spans. It also has a very tall first floor and a basement. So here's the structural parts. So it has a steel roof, which is put on top of the joists, which are rectangular steel beams. We took 5 times 5 centimeters, and they are placed in a quadrant of 3.5 meters, so the distance between them is 0.875 meters. And then those are put on top of the I-beams, which are very big. They're 1.8 meters tall, the web, and it has 50 centimeter wide flanges. And those are put on top of the cruciform steel columns. So we started out with doing this with a snow load, and we took one of the quadrants. There are 18 quadrants for each length, and they're 63 meters, by the way. So you take the area for the distance between one of those joists, and then you take them times 1.5 the snow load. And then for dead load, we calculated 1.25 for the steel plate roof, and then for insulation and the finishing material, 0.5 more, so 2 dead load per square meter. We put 1/4 on the corners and a half on the sides, and then we saw the weight of all of those ones. And then put them as point loads on top of the beams. So here are the beam loads, and we had 3 different sections. We made our own sections for the own IPE beams. And the yellow ones are 3 centimeters thick flange, so the height and the width are the same ones, but the thickness of the flange is the only difference. So with the yellow ones, there are 3 centimeter thick flanges, and then you see the magenta ones, there are 4 centimeters thick ones. Then the green, we had to go little by little up to 6.5 centimeter thick flange in order to calculate, and depending on the maximum bending moment on all of those ones. And then just for the record, with the point loads we put on each one, it's 24.15 kilonewtons for the snow load and 36.6 for the dead load. And the same thing there on the corner we put 1/4, and on the sides we put half. And then so we took the side beam. So side beam is one of the edge beams, which has a different bending moment than other ones. We know that they're supposed to be symmetrical, the diagrams, but for some reason they are not. With the one for 3 centimeters, the flange, it has a maximum of around 11,000, so it's safe for this one. And also the shear moment you see in the other one. And then for the middle beam, we took the last beam that was still yellow, or 3 centimeters, and here you see the maximum bending moment being 7,859. So it has a different profile. And then for the biggest one is of course in the middle, and you can see here that it has 18,300. And then for displacement, it's pretty huge because we made our own sections. And also the shapes are different and everything. So if you calculate if you take 63 meters and divide the 70 centimeter displacement, then you notice it's 1/90 seconds, so it's technically too high. So and also for a note with the self weight of the beams, so because we put such a ginormous column, so that means that we found out that the smaller beam is 5 kilonewtons per linear meter, while the magenta one is 5.73 kilonewtons per linear meter, and the big one is around 7.6 kilonewtons per linear meter. Another thing that we forgot to mention was that we calculated because it's 18 units times 18, so 18 times 18 times the 24.15 that we set for the snow load for each part. That's equals to around 8,000 kilonewtons. And if you check the equilibrium equation for the whole thing, it's 13,000 for the snow load, which is a bit of a difference. But then if you take 8,000 times 1.35, then you have around 11,000. So 11 and 13 or 11 and 12, they're pretty coherent. And then also regarding the dead load, that one's different because of course the dead load also includes the self weight of the thing. So in terms of that one, then we have 26,000 kilonewtons around that, and with the one we calculated, it was 15,000 about, but that is without the self weight. So if those numbers are correct, which they very well it could be, then the self weight of the structure would be 9,000 kilonewton. As we see in the displacement here, the biggest displacement is 70 centimeters, and with the span of 63 meters, that means 1/92, which is too big. But then again, we made our own sections, and that means that it's very possible that they were too big, and thus the self weight is overbearing. And that could be an explanation.